Today we're going to talk about section 7, which is about function operations. So we have 4 basic operations for like arithmetic. We have addition, subtraction, multiplication, division. Those are the same basic 4 fundamental operations for functions. So the function f plus g of x, I can calculate by just doing f of x plus g of x. Difference, if I have the function f minus g of x, that's the same thing as doing f of x minus g of x. For multiplication, if I have f times g of x, that's the same thing as taking f of x times g of x. And if we talk about division or quotient, f divided by g of x is the same thing as f of x over g of x, given that g of x is non-zero. For the quotient, why do we have this extra requirement that g of x is non-zero? Exactly. Can't divide by 0. You can't have 0 in the denominator. Those are both excellent and appropriate answers to that question. Very good. Everybody feel like nothing here is shocking, right? If you're talking about like the sum or difference of functions, all you do is add or subtract the individual functions. Yeah, it's okay. You can like push him down the stairs later or something, right? No, you were giving him a hard time. Is the whole soccer team like beat up? I saw Gabe came in with crutches.
Gabe's still on crutches?
Yeah, he was wearing crutches earlier.
I got kicked like right under like I was knee almost. I get hurt a lot. This kid like karate. Like no one even knows. It's his dad. He literally was talking about it. I don't know how that. I was just running. I threw up on that. And it was like, oh, because I was on the floor.
All right.
I put it walk.
So let's do just a couple of quick examples here. So let's say f of x is 2x minus 3, and g of x is the square root of x plus 2. And we want to find first f plus g of x using the rule that we had written above. Actually, let's do a different color here. Let everybody that's looking at these notes know that we have a question and an answer. We can just do f of x plus g of x. So when I substitute in the expressions, I know f of x is 2x minus 3, and g of x is the square root of x plus 2. And the only thing left now to do is any kind of simplifying or combining of like terms. Is there anything I can do here? Sure, Miguel.
So, for like the f of x, when we like plug it in, would you put parentheses around it?
You can, but because of the addition, we don't need to do that. It's not incorrect to do it. But since the operation in between them is addition, and addition is purely commutative, we don't need the parenthesis there. It's not wrong to put it, but it's unnecessary for addition. but that's a good question. So the last thing we'd need to do here is to do any simplifying or combining of like terms if possible. Is that possible in this case? No. So that's it. That's done. Let's do g minus f of x. So, using the rule that we stipulated above, that's the same thing as g of x minus f of x. So when I substitute in, I would write this. Is this correct? Miguel? Is what I wrote correct? Yeah, there needs to be a parenthesis around that 2x minus 3 because subtraction is not commutative, right? A minus b isn't the same as b minus a. When we make that substitution, we need to make sure we include a parenthesis around, especially the second term, because our first step to simplify would be to distribute that negative. And then, is there anything else we can do? No. So we'd be done at that point. Is everybody okay with this so far? Again, nothing terribly, terribly unfamiliar or should look really very difficult even. It's just good to review some of this stuff because some of these little tricky things that are like, oh yeah, I need to make sure I put a parenthesis there and distribute the negative. Like, easy to forget those sorts of things. So that's why we're doing the examples here. If I want to do g times g of x, that's going to be g of x times g of x, which is square root of x plus 2 times square root of x plus 2. Can I combine those? Yeah. So that's the square root of x plus 2 squared. Yeah, which is just x plus 2. Again, I showed maybe more work there than was necessary, but I didn't want anybody looking at their notes to be like, where is this magic coming from? You know, so maybe I did a little overkill there, but I tried to do that on the notes, right? Overkill it a little bit. Those of you that have had me before know I like to write notes. Let's say we want to do f divided by g of x. So that's the same thing as f of x over g of x. That's 2x minus 3 over square root of x plus 2. Can I do any simplifying here? So, like, you could rationalize the denominator, like multiply the top and bottom by square root of x plus 2. But is that really does that really make it any simpler? Probably not. Let's leave it here. In general, unless really instructed otherwise, if you're talking about an algebraic expression that involves variables, I wouldn't bother really rationalizing denominators. If it's a numeric expression, like 1 over the square root of 3, there I would rationalize the denominator. And even in those cases, like the deeper you get into mathematics, maybe the less frequently this happens. Like if we're taking class like Calculus 3, I wouldn't even bother with any of that stuff because it usually just makes everything worse. So it tends to be a convention early on, and then that's a convention we a lot of times end up dropping. So I'll let you know when it becomes a frequent occurrence whether I'd expect that to happen or not. Everybody happy so far? This should feel pretty familiar and pretty easy, right? There's a fifth operation for functions that doesn't have a numeric corollary. Does anybody remember what that might be? Okay. Composition. And what this says is f compose g of x equals f of g of x. Don't say fog, it makes me want to fight you. Last hour was really convinced that they were going to try to fight the entire class on me. Everyone wanted to call this fog. It makes me so angry.
What is the appropriate?
So you would say f compose g. That is just the symbol that they used. If you see it typefaced, it's definitely not an O, but because I can't write in typeface, yeah, it just makes me angry. All right, let's do an example to just kind of refresh how we do these compositions. So let's say that f of x is 2x squared minus 3x, and g of x is negative 3x plus 4. And then let's just practice a couple of compositions here. So we'll start with just f compose g of x. So according to the definition that we stated above, that's just f of g of x. Now what I like to do is I like to replace g of x with its expression that it's equal to. So I have f of negative 3x plus 4. And then what I like to do is I like to rewrite f of x, except wherever there was an x, I'm going to write a parenthesis. And inside that parenthesis, I'm going to place that expression for g of x. Everybody okay with that? So really what are we doing? We're taking the expression for g of x and plugging it into our expression for f of x. Okay? So, last thing I would need to do here is any simplification. Is there simplification that can happen here? Yeah, what's the first thing I would need to do? Distributing is not the correct answer. Foiling is. Remember the order of operations. I should deal with that exponent before I deal with any multiplication. And remember that exponent around a binomial like that indicates FOIL. So again, when we talk about FOIL, this is like the only time that I'm going to, the entire year, probably write out a FOIL for you guys. So let that soak in and enjoy that. So F is for first. We multiply those together. We get positive x squared. Then outers is negative 12x. Inner is negative 12x. When I combine those together, I get negative 24x. And then last is 16. Everybody okay there? Oh, thank you. Somebody's paying attention. Appreciate it. But it made life really difficult later on when I had to flip all the signs because I did it wrong. Ay, ay, ay. Now it's time to distribute. Whoop, 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 whoop. So 18x squared minus 48x plus 32 plus 9x minus 12. And when I combine this all together, 18x squared plus 39x plus 20. I'll scroll that up for the people playing, like, dodge the head in front of me there. Maybe that makes it a little easier. The good news is that there's always my notes in the video posted to Power School, even if you're playing head dodge the whole hour and you're like, this is so frustrating, I quit. So. Oh. Just like that? I was making a joke like the rap song. When you move, I move. Well, anyways, all right. It's old. It's old. I'm old. That. I quit for today too. All right.
Is it minus 39x or no?
Yes. Thank you. Thank you. Again, please double check me. I do make mistakes. If you think I make a mistake, don't hesitate to ask. Even if it was correct, it usually is something worth talking about, because if you think it's wrong, you're probably not the only person that's confused on what's going on. Please, say something. All right. You think your knee hurts now. You just wait. Good gravy. All right. So that's g of f of x. I mean, it's funny, isn't it? Everybody knows this is a joke. You're all laughing and smiling. I think it's going to be okay. So that's g of 2x squared minus 3x. I'm going to go ahead and rewrite my g of x, but wherever there's an x, I'm going to put a parenthesis, and then I'll write that expression for f of x in the parenthesis. All I have left to do now is to simplify. To simplify this, all I need to do is distribute, some kind of multiplication. Right? I did that right, didn't I? Yeah. Okay. It's been a long couple of days here. Don't you start with me. I just fail to understand why this is so funny. So, if I want to do F compose F, same kind of thing. You guys. First thing we need to do here is to FOIL. I'm going to do this foiling in my head. I told you before that was the only time all year you're going to see me write out a FOIL. Yeah, you heard it. So that's 4x to the fourth minus 12x to the third plus 9x squared, and then all this googly-gock here. And then we'll do some distributing. And when I combine this together, 8x to the fourth minus 24x cubed plus 12x squared plus 9x. Whew. That was an irritating problem. A lot of symbol pushing there, right? So, you have a question? No. Okay. So the question becomes then, why bother with this composition thing? What is this useful for? Does anyone remember? We all talked about it last year in Algebra 3-4. So this definition says let f and g be functions. We say that g is the inverse function of f, provided that f compose g of x equals g compose f of x, which is equal to x. So this composition is important because it's part of our definition for an inverse. It's how we would prove two things are inverse of each other. Yes. And oftentimes, what do we call G if it's the inverse? We would call it F inverse and write it with the negative 1 exponent. Note that that doesn't mean 1 over F. So F inverse of x is not the same as f of x to the negative 1. This one is the inverse. This is a reciprocal. Okay, just to clarify some notation there, that's easy to get mixed or turned around on. Miguel, you were asking something?
So it only works if it's inverse, right?
If this relationship is true, they're inverses, and if they're inverses, that relationship is true. So it works, it's an if and only if statement, it works in both directions. So this definition is nice in that it provides an algebraic way to verify if two things are inverses, or gives us a property that two inverses possess, but it doesn't really tell us like what we mean by an inverse. So let's kind of look at a more conceptual description of what this is, or what we're talking about here. So let's say this is our function f. So what this is saying is that f of 1 is equal to 4, f of 2 is equal to 5, and f of 3 is equal to 6. Everybody agree with kind of what this picture is kind of representing? Oh, thank you, yes. Again, you think I make a mistake, please tell me, especially by the time the last hour of the day runs around and my soda pop's wearing off. Become, what? Well, he's catching all the mistakes. It's because he's sitting in the front row and can see now. Okay. So if we go back to our definition of an inverse, if I wanted to do g of f of 1, I would need that to equal 1. If g is an invert, if g is f inverse, then g of f of 1 needs to be 1, g of f of 2 needs to be 2, and g of f of 3 needs to be 3. Right? That's what the definition says. Everybody okay with that idea? Okay. So if I were to draw that picture, this is going to be my G. F of 1 is 4. F of 2 is 6. And f of 3 is 5. So f of 1 needs to go to 1. F of 6 needs to go to 2. F of 5 needs to go to 3. So what are we really looking at when we're looking at the function and its inverse? Yeah, right, this is f inverse. What really happened here? Yeah, we just flipped the x's and y's. Everybody's okay with that idea? That helps a little bit conceptually to show that that definition that we gave with the compositions is really saying the same thing as like the common sense way we approach this in our Algebra 3-4 class where we're talking about just flipping our x's and y's to find inverses, right? Then you can go to the restroom. I do not have any tissues. I have sheets of computer paper if that'll do.
I think paper towel would
probably be a heck of a lot more comfortable, yes. You're welcome. Another way we might represent a function instead of writing it as a mapping diagram, we could write it as a set of ordered pairs. In this case, if we were to find f inverse, what would f inverse be? Good. 4, negative 2. 6, negative 1. 8, 3. Good. And 8, 5. Everybody feel okay here? Do you notice anything about this f inverse that's potentially problematic?
Oh, yes.
What do you notice?
H has 2 lines.
Yeah. So here, f inverse was not a function. Notice in our previous example, was f inverse a function?
Yes.
Yes. So it appears that sometimes these inverses will be functions, and sometimes they might not be functions. It would be nice to find a way to predict when that happens. To do that, we're going to need some more definitions. Okay? So we're going to define 3 things here. Yes. So a function is called onto, or sometimes we'll use the word surjective. It's probably about a 50-50 split between resources, whether they call this term onto or they call it surjective. If every element in the range is mapped to by some element from the domain. Basically what this is saying is everything in the range gets used. Okay? So you have to have a way to get to everything in the range. Right? If I pick 7, there has to be some x that gives me 7 as an output. Everybody okay with that idea? Okay. The next definition, we say a function is called one-to-one or injective if every element in the domain maps uniquely to distinct elements in the range. Or in other words, no y-coordinate is used more than once. Okay? So no repeated y's. Definition 3. This one's not very complicated. Uh-huh. So if a function is both one-to-one and onto, that function is called bijective. Okay. Onto or surjective. Yep. So let's look at some examples of functions that are, injective or are onto but not one-to-one, or one-to-one but not onto, or both, and look at how that impacts the existence of an inverse. Everybody okay with that plan? So for the time being, I'm going to use mapping diagrams because I think it's the easiest conceptually to deal with. But we'll do some examples of these things looking at graphs and some other forms here in a minute. Okay? But we're going to start with like a mapping diagram. Just call this function f. So first things first, is this a function? Right, this is a function. Is it onto? Yes. If all I need to check is that everything in the domain is paired to from something, or everything in the range is paired to with something from the domain. All the y's are covered, so that's onto. Is it 1-to-1? No. And the reason it's not 1-to-1 is we have a y-coordinate used more than once. Okay? Let's look at what F inverse would look like then. And I've heard somebody already say, or multiple people already say, that we notice that F inverse here, not a function, is it onto? Yeah, everything in the range has got an arrow going to it. Is it 1-to-1? Yeah, each y-coordinate is used exactly once. But the key here for our purposes is that this wasn't a function. Okay? So this is example 1. Everybody's okay with this? So we saw something that was a function, it was onto, but it wasn't 1-to-1. This one down here, I think to be bijective, it also has to be a function. Right? So the definition requires a function. The up for injective and surjective, or 1-to-1 and onto, also require to be a function. Oh, so you're saying that these don't apply anymore? Yeah, that's probably fair. That's fair. Good point. All right, let's look at another example. Let's look at this. Actually, let's call this guy G. We'll use a different letter here. Is this a function? Yes. Is it onto? No. Why not? Yeah. So that's 7 in the range isn't used. There's nothing that goes to the 7. So that's why it's not onto. Is it 1-to-1? Yes. Okay. Now let's look at G inverse. Is this a function? No. Why not? Yeah, because not every x has a y. So the other stuff doesn't apply. Let's see, how did I do it before? Did it this way, I think. Because again, 1-to-1 and onto are respective to functions. Everybody okay there? Okay. If we have something that's both, A, B, C, D, E, F, G, H is the next letter. So H is a function. Is it onto? Yep. Is it 1-to-1? Yes. If I look at H inverse now, this a function? Is it onto? Is it one-to-one? Yes. So hopefully at this point you can see why looking at if something's one-to-one and onto is important for also looking at its inverse, since those are the predictors, or the necessary conditions, I should say, for its inverse to also be a function. Everybody feel okay about what we mean by one-to-one and onto, at least as far as a mapping diagram means? Okay, let's look at a graph. Is this a function? Everybody agree with that? Yes. Is it onto?
Yes.
No.
No. It's not every y.
Yeah. So if I pick, say, this y coordinate, there's no x value that gives me that. Everybody see that? Is it one-to-one? Nope. If I pick this y coordinate, it's used by two separate x's. Everybody agree with that? So what would I expect if I looked at this inverse? It should not be a function, right? Just for the sake of argument here, its inverse would look something like this. We're not going to talk about how to do that quite yet today. I'm just worried about looking at things and identifying one-to-one and onto right now. Okay.
So if it's not one-to-one, it's never.
Correct. Yeah. Good. So Michael said this was a function. He said it's onto, and he said it's one-to-one. We know it's one-to-one because the entire y-axis is covered. You can pick any y-coordinate you want, and you can track it over and find some x-coordinate that will cover it. Everybody agree with that? Furthermore, it's one-to-one because there's no horizontal line I can draw that's going to intersect the graph more than once. So let's see. We've seen yes, yes, and no, no. How about this one? Good. So definitely a function, right? Would pass a vertical line test. It is it's not on, it is onto, because again, the whole y-axis is covered. An easy way to check that is if you have a continuous function with one arrow that points up and one arrow that points down, you got something onto there by the very definition, like it's got to be onto. It's not one-to-one though, because say this y-coordinate here is used by multiple x-coordinates. So a horizontal line test can tell you if it's a one-to-one or not. Okay? So now I have to do not onto but one-to-one. Okay. Well, that just gave it away. Sorry, guys. Oh, you know what? Let's do this. That's less of a dumb one. So yeah, that is a function. It's not onto, right? Because, again, you could pick any of the x's down here. I'm sorry, any of the y's down here, and there's no x that can give or that pairs with those y's. It is one-to-one, though, because, again, it would pass a horizontal line test. Any y coordinate I pick is going to intersect or going to be used at most one time. Everybody okay with that idea? All right. We're stopping here. This looks like a good spot to stop.